what I'm going to be talking about is ecological networks. And let's see, here's one right here. We have almost a iconic complex system. We have high-dimensional chaos going on here. You have plants growing at a certain sort of rate, being eaten by herbivores, being eaten by carnivores. That's like a parasite eating an omnivore up there. Basically, we have a fairly complex structure of a network and the dynamics that result from it. And I think it's a wonderful place to discuss complexity. I love complexity, sort of. If we'll be getting back to that as I've titled the talk. We're talking about complexity in ecological networks, friend or foe, but what I'm thinking is, of course, that it's friend and foe. I've got this sort of mix of a very reductionist attitude. It's like, if it's complex, it's just you don't understand it. You get show some imagination, simplify it, find the laws that allow you to predict its behavior. And so that's sort of, that's the faux aspect. But of course, I'm inspired by it, and I love complexity. And you get a lot of money if you, or you get more money if you study complexity. So both friend and foe. Now, my research agenda is classic complexity science, where you scale up interactions between a couple of nodes within a network. In my case, they're species. Use networks to scale them up to be able to understand the behavior and dynamics and hopefully be able to predict complex systems. This is a lovely classic 1500s depiction of food webs, and it's a delicious mix between society and nature. This old guy is explaining to his son, it's like, look, I've always known that the greater fish consume the smaller ones, and it's the parable of society and how little people get squashed and eaten by society. The kid says, yeah, I see it, I know, pointing over there. And so that's I think that is still within us. We talk about where we are on the food chain, in society, that sort of thing. Back in the 1500s, they were on that concept. Back in 1990, one of the first real good food webs we saw in our ecological literature came from Kirk Weinmiller, who spent a long time down in South America documenting these river food webs. And his conclusion was basically, it's variable, it's crazy, as this diagram suggests, it's pretty much intractable. Then Peter Jozes, a more theoretical ecologist, came along in about 2000, and he wanted to know if he could use theory to predict whether, if we wiped out these African fur seals, if the fishing industry would get more fish, anchovies, for instance. And his conclusion is like, given that network, given our theory, we don't even know the direction of the change that removing that seal would have on the abundance of fish. Hence, diffuse and largely indeterminate. So we have these different pictures of these ecological networks, from rather immoral to intractable to indeterminate. And so that sort of sets where you're going to try and pull some science out, where me and my colleagues are trying to pull science out of. And basically we're thinking that actually they're beautiful, they're tractable, they're scientifically productive, and I think a lot simpler than they have been made out to be. So here's the food web that I pictured. It's of Little Rock Lake, Wisconsin, put it together as a master's student, where we have the plants, algae in a lake depicted at the base, bunch of invertebrates, zooplankton, the herbivores above, some more other invertebrates above that are more carnivorous, and a fish and a leech. The fish eats the leech eats the fish. The wonderful little nose rings there are cannibalism. And so this is what a good, where we're starting to get reasonably true or faithful pictures of ecological networks. We're really assembling the the understanding we have of these networks. That gives you a picture of it. And so one of the things we discovered looking at that is a basic measure of complexity that has become pretty much the most used in ecology, and that is this idea of connectance. It's the fraction of all possible links within a system that are realized. If everything ate everything, including its cannibalistic self, you'd have a number of links equal to the square of this number of species. Instead of that equaling 1 or 0, we have connectance empirically ranging from 3% to 30%. So that's at least a measure of ecological complexity that we have. And if we look at all these different food webs we have, at least as a graduate student again, it's like, don't even try to look for any regularities. The only law in ecology is that it depends. And I'm like, yikes, that hurts. I want to be a scientist. That sounds like natural history. And so, but anyway, I went ahead and did it, and worked on them. And one of the things we discovered was that if you normalize for the complexity, you find that the distribution of specialists and generalists are remarkably similar amongst a bunch of food webs. That it's pretty much like, hey, we have a few generalists, lots of specialists, and at least in a statistical way, there's a lot of consistency amongst these apparently variable networks. Another is, rather than just statistical understanding, I wanted to generate some mechanistic understanding about these networks. And we did that by creating the niche model that characterizes particular mechanisms that are operating within nature that give rise to the systems we study. Well, first of all, there's a hierarchy, and it's pretty obvious. You have plants, they're eaten by herbivores, omnivores, carnivores, and so on. Plants are the ultimate source of energy, or more generally, autotrophs. It might be down at the sea vent where you have chemoautotrophs, whatever. You have some basic source of organic energy upon which everything else depends. We also think of it in terms of big things eating little things, that there's a hierarchy in terms of body size as well. And we represent this hierarchy as everything is on a line from 0 to 1. We call it the community niche space. Each one of the species in the system are represented as a triangle there, and we place them on this axis. And each species tends to eat species lower on this axis, on this dimension. And so one thing about what they eat is that they get to choose a contiguous range. They can't pick and choose anything. They get a range, eat everything within it, don't eat anything outside of it. And so you can think of that in terms of if something eats big things and little things, they also eat medium-sized things. And then there's the variation that we see is almost entirely between a couple of stochastic things, like where you happen to land there, and then how much many species, number S, and how much complexity in terms of connectance. If you have an empirical food web, give me the number of species and the connectance, feed it to this model, it creates a food web that we claim looks a lot like what we see in nature. And the way we do that, the rules that institute those that describe those mechanisms is that each one of S species gets a uniformly random number between 0 and 1. Each species gets a range. It's a feeding range between 0 and 1, and then you just place that range on the axis by choosing its center to go somewhere between the range's owner and half the size of the range so it doesn't fall off. And that's it, right? That's kind of simple, right? There's 3 rules: random number, give everyone a range, it comes from a beta distribution, and then place it there, and you do that for all the species, and you create a food web. And it does really well. We thought we need many dimensions to do food webs. One dimension was simple enough. We've tried to even improve it. You can add some more variables, some more bells and whistles, and it really doesn't do that much better. The one thing I'm going to go into is my favorite accomplishment of the model is that it predicts these half-billion-year-old food webs, predicts the structure of these half-billion-year-old food webs. Back when Dr. Seuss creatures such as hallucinogenia or Anomalocaris swam the oceans and ate trilobites for a living. Some wonderful paleobiologists, namely Rachel Wood and Doug Irwin, they've spent much of their careers studying the Chang-Chang shale and the Burgess shale that basically documents these food webs. If you look at their structure, you find out it looks a lot like modern food webs in that if you give it the number of species it has and the amount of connectants, then the niche model does pretty good at predicting it as it does modern food webs. So here's some observations of some of the statistics we describe with food webs: the fraction of species that are top, intermediate and basal species, fraction of species that are herbivores, cannibals, the variability of generality, path length, clustering coefficients, a whole bunch of numbers that you have an observed of the web. You have the niche model. When you run it 1,000 times, it has about an average a value of each one of these parameters, and then it has a variability and where you can decide whether the observation falls within the niche value by graphically what does it fit within this bullseye. You expect 90% of your observations to fit within there, 5% out of there. There's more like 15 or 20% outside of the bullseye for both the modern food webs and the Cambrian food webs. But by and large, the big conclusion is that the similarities much outweigh their differences. And so there's a bunch of details that, what was that, the rules that you're supposed to attend to in one of the talks. Obviously, I'm not telling you a lot of caveats. Please ask questions at the end. But I think we found that this work shows that food webs are simpler than we thought. They're consistent amongst habitats across space and across quite a bit of time. The question is, what's useful? And I loved the statement of some of the feminist critiques of science saying, come on, there's a social duty here, which is like right on. Yeah. And so if we take the equations, I sort of boom, 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 boom. Yeah, let me just go to this side. Okay, so to get at what we really want to know, we want to know about the dynamics of these ecological systems. Will we have enough food to eat? Will enough carbon be pulled out of the atmosphere for us to avoid getting our butts cooked off the planet? And let's see, so how does architecture influence dynamics? There's a bunch of sub-disciplines here that is kind of within this discipline talk, but I'm just going to skip by that and go to this this depiction where I can go back to how do you go from structure to this, dynamics. How do you calculate the changes and predict the changes in biomass that result from the structure these organisms are embedded in? And so this is the basic equation we use. It's an ordinary differential equation that describes the rate of change of each species' biomass as its growth if it's a plant, minus, so for all animals, they don't just grow like those autotrophs. That is a zero term for them. But all the animals you lose according to your metabolic rate times the biomass being maintained. That's sort of that's a measure of activity of the species. Then you add everything it eats and you take away everything that eats it. That's pretty simple, right? You have a metabolic cost of staying alive, you get to eat, and you are eaten. And back to that big fish eating little fish diagram. Let's see, the plant model is a bit different. First of all, they don't have a metabolic loss, they don't eat anything, they're just a logistic growth equation with a community level carrying capacity. Animals, they have all of these other terms. They have maintenance costs. They eat and are eaten. A key part of this equation is metabolic rate. And so this A shows up here in a couple of places. Basically, you have the metabolic rate times the species biomass. That's how much activity. That's like, to me, that's the verb. You see out there, you look at nouns, what's it doing? It's got an activity times its abundance. And this is a key activity, is it's eating at its maximum maximum consumption rate times a functional response that tells you how much of that maximum rate it realizes as a function of how abundant its food is. If it doesn't have any food, it better not be eating anything. If it has a lot of food, it's eating at its maximum rate. The way you get between 0 and your asymptote is where a lot of biology is. It's where do things fight, do they hide, a whole bunch of stuff in there, wonderful experiments that I'm just going to gloss right over and get right to a key parameter, metabolic rate. And productivity for plants. It's very conveniently estimated just on the body size. You tell me how big something is, I'll tell you its metabolic rate. With of course, this is a log-log graph. A lot of suspicion should be put there, but still, these are fairly easy to estimate parameters. And so we have a wonderful history of ecology from theoretical ecology from which these equations are derived. What we've done is we've scaled it up to complex systems. And so one thing what we've done is we've done these experiments where, in silico experiments, where we will take out a species, where is it? Remove it here. Boom. Okay, we've removed a species. And in ecology, a famous way of calculating the strength of an interaction of a species with the other species in the community is by take it out and see what happens. If you take it out and nothing happens, you got a puny little strength. Take it out and a lot of stuff happens, species change their abundance, they might go extinct or something like that, then that's a big effect. And so we've create many different webs with empirically reasonable body size ratios, and we take species out and we measure its effect. In this case, I'll show you in the back, this omnivore that sort of parasite ate is going to get really abundant. It's going to start chowing down the food, and a bunch of these other species are going to go extinct. The difference between the abundance of a species with that removed species present and with it absent, that's a measure of its interaction strength. We did a bunch of computational experiments in, doing that. That's what this paper describes. And we came up with a pretty simple algorithm for estimating interaction strength in the computer based on the body size of the species you removed, its abundance, and the abundance of the species that you're looking at the effect on. So how big is the thing that you removed? And experimentally, it's this whelk that likes barnacles and mussels, that likes mussels. And they did some, Eric Burlow did these wonderful field experiments on it. And so what we wanted to do is see if the algorithm that applied in our computer for estimating interaction strength accurately estimated the one that Eric observed in the field. We used pretty much the whole framework that I just described, and these are the results. If you put our predictions that we got out of the computational models on this graph, you find that depending if the removed species was high or low, you would get these different strengths of interaction as a function of the abundance of the organism you're looking at the impact on. So there's more, there's less. And the overlap between the predicted and observed is, Eric especially, spent like over half a year just making sure there wasn't a tautology there. This stuff doesn't look, you don't get this stuff as good in ecology often, and it's immediately suspicious. But so that's just a point. I think we've got onto something with respect to dynamics. So here's the iconic sort of almost physics experiment applied to a lake that was incredibly well studied. Over 20 years, they've bi-weekly sampling of this lake. We have this nice kind of regular looking food web that the folks observed in this lake, a bunch of algae, some rotifers, some ciliates, mostly microbes here, and then we get up to the fishes. Over 20 years, this is the relative biomass. Lots of bacteria, some crustaceans. Fish are fairly abundant. There's these rotifers and ciliates that are very rare, but there's some big links between them. So in terms of dynamics, we think about, can we forecast the dynamics? Here's the empirical time series. This is the average of all 20 years. That in the spring, phytoplankton grow, the herbivores get happy, they knock down the phytoplankton in this clear water phase. The herbivores get nailed between lots of no food and lots of their predators. They get wiped out, the phytoplankton recovers, and you go on into the fall. So this is just a classic year. What we did was take each species average abundance during each of these phases and convert, we first of all parameterized a model, our model, with the initial biomass in the spring and their productivity and their metabolic rates as you would estimate from their body size. And this is what the data look like when you make that same data one abundance per phase. What happened? Did something get... Pardon me?
The mouse is on that screen.
Yeah, I'm just trying to get back to let's see. I think it just canceled. It just killed the whole thing. Okay, so let me get my... Sorry about that. Go back.
Do you want to give a slide list last 30-second conclusion?
Yeah, boom, 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 boom. Okay, I think so. Here, just... Boom, okay. Let's see. So, here was the data. Here's the blown up, let's see, the rare species are blown up to see better. This is the prediction from the model. You have a high degree of similarity between what was seen and what's predicted, just starting out with some initial conditions and letting it roll. So let me go, I'm going to skip the fishery part. We've added fisheries to this, this model, basically the human interaction. We found some cool results that got some lessons, but hey, I think what we're doing is we're establishing some mechanistic foundations for sustainability science. We've got these multiplex ecological networks. The multiplex part is when we use life stages to represent maturity rather than eating. The connection between two nodes is something grows older and becomes more mature. And we've got some key parameters provided by this theory called metabolic theory, and it explains and predicts ecological services, ecosystem service. So so you can see that I had this goal. I want to simplify complexity, generate new understanding, predict what couldn't be predicted before, and contribute to really, I mean, this is what motivates us to, many of us, to contribute to a more sustainable, just, and verdant world. And then in terms of just beauty, hey, there's a balance of nature out there. What is it? And I think this gets at that. In terms of complexity science, I think we've shown how in our work that actually increased complexity increases predictability. That complexity is rather easy. Well, I would say, relatively easily reducible, and we can use that to, let's see, apply network science to complexity. So finally, I just want to say I love that idea of pernicious reification, and you got to watch out. I really like that model that I showed you. But I think what we're up to here, we're adding economics to these systems and other things. We're engaged in a much more creative community reification. I'm not sure that's any less pernicious, but I think it's a fun and worthwhile activity. And I hope I have time for a question.
Yeah, thank the speaker. We're going to have time for one or two questions while we set up for,
Yes.
is Jessica here?
Cool.
If Jessica Wilson's not here, then we're going to have Kai Jun speak, guys. And yeah.
Thanks for your presentation. Unfortunately, I missed the earlier part. I'm François Diaz-Morin. I'm at CSAC. I will later on present about societal metabolism. So it's, but about your last comment, why is it necessary to put the economic value on your model? Why is that?
Get people to pay attention to us is the quick one, because when we want to, necessary, I don't know that it is necessary. I'd love for a Gandhi or Martin Luther King to come out here. It isn't about making money, it's about nature has rights. Unfortunately, I'm not a Gandhi or a MLK. I haven't seen one emerge. So the way to get people to pay attention and perhaps change their behavior is by putting money on it, putting a price on it. I'm not positive that works. I know it can work against us. I don't say it's necessary. There was another.
Thanks, Neil. That's really great ideas. And so my question is, so in these systems, in the Constance Lake, for example, it's rather isolated system. What happens when you have metapopulation dynamics? You have more than one single node. You have a interacting metapopulation.
Then in multiplex terms, you get another layer. You get migration. And it's, to me, it's fairly easy. I mean, come on, critters move from one thing to another. You have to go ahead and specify the function by which, if it's more likely to move when it's hungry or less likely to move when it's, you just specify those. So right there, what I showed was very much a foundation, a kernel onto which to build many other things. And going to metapopulations is, to me, at least theoretically, totally straightforward. Many of us are already doing it. Yeah.